Okay, wow. So higher regularity. Okay, so now we will turn to well postness in HS for s greater than one half. So the theorem will be that for every s greater or equal than one half, the conclusions of theorems. Well, let's name it 1 and 2. This is local well postness. This is global well postness for h1 half. So the conclusions of those theorems were h1 half, and well, let's put that is always in R3. This h1 half in R3 and h minus 1 half in R3. In theorem 1 are replaced by HS R3 and HS minus 1 R3 respectively. Okay. To prove the theorem, we need the following generalization of lemma 1 of the first lemma of local well postness. So we have that lemma 3 will be for mu greater or equal than 0 and s greater than equal than 1 half. The map, well, what we've been calling JU, is by definition E minus mu x absolute value convolution u squared u is local Lipschitz. Okay, Lipschitz from HS Rn into itself. Okay, and with, well, Ju minus Jb now in HS is less than equal, then u norm squared HS plus b squared HS, okay, and u minus b HS. This is for all u could be in HS R3, and moreover, we have that norm of Ju HS is less than equal within a constant, okay, to u squared HR, okay, and we will see what it is that R norm UHS holds for all U in HS where R is going to be the maximum of S minus 1 or 1 half, okay. Okay, so we only show the second inequality since the first one can be proved in a similar way than lemma 1, okay. So we'll prove this one, okay. Okay, so we have mu greater or equal than 0, s greater or equal than 1/2. We define again the alpha as mu squared minus Laplacian alpha over 2, and we're going to try to get a bound for JU HS using, as we did before, that we'll try to obtain this kind of bound. JU norm 2 plus, as we did before, DS JU, okay? Norm 2. We're going to use this. So recall that we had that when we have d alpha with alpha equals to 2, this would represent e minus mu x of x when we had the convolution. This d with the convolution of another function. In our case, it's going to be u absolute value squared multiplied by u. Okay, so using that, now we have that ds ju, okay, is less than equal than norm. This is norm 2 on ds d minus 2, because what I just say of f is u absolute value squared u okay, so well, let's put this parenthesis outside, okay, and norm 2 parenthesis goes here because the convolution is only with u absolute value squared. Okay, so this will be less than equal, now using Leibniz rule, okay, the generalized that we used before. Now we will have P1 Q1, okay, and P2 Q2 will be infinity and 2, and the alpha will be 0 again. Okay, so we will have this less than equal, then ds minus 2. Okay, now we can take these two together, u squared p1 u q1, here we're using alpha equal to 0, plus d minus 2 u squared norm infinity, and ds u norm 2. Okay, in this side we use that beta is equal to 2. Recall that 1 over p1 plus 1 over q1 must be 1/2. Okay, this follows from using infinity and 2. Okay, so this will be less than equal than the same here. Okay, p1 q1 plus, and first let's see how we found this. So recall that in lemma 1 we had this factor norm infinity, and we bound it by minus Laplacian 1/4 u squared. Well, recall that this is d minus 2 u squared norm infinity, so we bounded by this, and then in lemma 1 we proved that this is less than equal than norm u 2 squared h1/2. So we first bound the first term by u square h1/2. What happened with this one? So recall that in lemma 1 we proved that well, basically that d1/2 u in norm 2 is less than equal within a constant than u in h1/2. Okay, so if we prove lemma 1, but in the case for instead of 1/2 ds u, we will have the same bound, but for hs. Recall that this comes from the first bound that we wanted to see that that u norm 2 plus 1/2 u less than equal to u h1/2, and we want to make the same. We have to consider s here and s here, so we will use that. So this will be less than equal that u in hs. So let's plug that norm u hs. Okay, so let's see how can we bound this term. Okay, to control this term, we will have two cases. The first case is, let's say, for s between 1/2 and 3/2. We choose p1 3 over s and q1 6 over 3 minus s 2s. Okay, so we will have ds minus 2 u. Okay, just plug in now p1, which is well, let's say 3 over s. Okay, 3 over s, and then I plug in 6 over 3 minus 2s. Okay, for that bound we will use the weak-Young inequality, recalling that the es is representing a convolution. Okay, so this would be less than equal within a constant. Then recall the kernel g mu 2 minus s. This was minus alpha 3 1 plus s weak. Okay, multiplied by u squared absolute value 3/2 UHS, and we'll see where all these come from. Okay, so first, these two come from the weak-Young inequality. Weak-Young's inequality tells us that 1 over p plus 1 over q is equal to 1 plus 1 over r, where p is this, so we will have 1 plus s over 3 plus this is 3/2, so we have 2/3. This will have to be 1 plus 1 over r, and r is 3 over s, so it has to be yes, equal to 1 over this, so over 3, and you can see 2 plus 1, this will be equal to 3 plus s over 3 is the same as this, so this is a correct use of Weak's-Young inequality. So this is Weak-Young's inequality, and this bound that comes from the bound that u 6 3 minus 2s is less than equal within a constant than uhs. Okay, this is a Sobolev inequality. Okay, recall that this Sobolev inequality is valid for s less than 3/2. Okay, so that's why we have a first case. We have a second case when we will see what happens when s is greater than 3/2, so that we can have the other Sobolev inequalities. Recall that 3 is the number, is the dimensions, so in this case 3/2 will be the critical case. Okay, so this will be less than equal than norm u square h1/2 uhs. This is bounded by this. This is a Sobolev inequality. 2 less than equal than 3/2 equal than 3. This is for s less than 3/2. This is 1/2 in this case. And this remains the same. In the next video we will continue with this bound and make the second case. Okay.